I'm Tim Ventura, and we're joined today by Dr. Aubrey de Grey, President and CSO at the Lev Foundation and co-founder at the SENS Research Foundation. Dr. de Grey is the author of the Mitochondrial Free Radical Theory of Aging and co-author of Ending Aging. He's one of the world's leading experts in longevity research, a fellow of the Gerontological Society of America, the American Aging Association, and also the Institute for Ethics in Emerging Technologies. Dr. de Grey has a BA in computer science, studies in bioinformatics, and a PhD in biology from the University of Cambridge. Before we get started today, I want to add a disclaimer that our discussion is about ongoing scientific research and we are not providing medical advice. I think it's also important to remind viewers to consult their doctor before starting any supplements, beginning an exercise routine, or undertaking lifestyle changes. So Aubrey, welcome back. It is truly an honor to have you with me today, sir.
Well, thank you. I'm delighted to be here.
Well, so your work in longevity is absolutely legendary. You are one of the top researchers in the world. And so, again, I can't thank you enough for your time. You are both the co-founder of the SENS Research Foundation back in 2009, and then your current work is with the Longevity Escape Velocity Foundation. So I'm wondering, can you bring us up to speed on the Lev Foundation's goals and the recent achievements that you've had?
Sure. So the goals are, of course, the same as ever. I want to hasten the defeat of aging. I want to bring aging under comprehensive medical control as soon as possible. And I want my organization to contribute as much as possible to making that happen. So the main thing that distinguishes Lev Foundation from any other organization in this space right now, including SENS Research Foundation, is that we are focusing very strongly on combinations of interventions. We don't do experiments with people. We only do preclinical work in the laboratory, so we work with mice. But we're interested in what happens if you take things that already have some benefits in mice individually, and you put them together in the same mice at the same time. And this is something that really, its time has very much come because there are quite a few things that have shown promise individually. But it's something that is not really aligned with the incentive structures of organizations that are funded by the government, for example, or for that matter, with organizations in the private sector. It's not, no one's doing it. At SENS Research Foundation, we focused on other things that are also not really aligned with the incentive structure, namely the development of damage repair approaches, which is, of course, what my research has been about for the past 20 or more years. But damage repair approaches that are very challenging to implement, things that basically other people weren't working on simply because they were too hard. And if you want to make money sometime soon, or if you want to get your next grant application funded, then get papers in high-profile journals very frequently, then you don't work on the hardest stuff, you work on the lowest hanging fruit. But the hardest stuff is just as important because this is a divide and conquer approach where we've got to get everything working. So what SENS was doing and is doing is certainly valuable in its own right, but someone's also got to do this combining thing, and so that's what Lev is doing.
Well, I want to jump into the baby boomer demographic. So they are currently between 66 and 77 years old in the U.S. So the demographic is aging, and they are responsible for funding a lot of the current booming medical research that is going on in longevity. As they continue to age, do you expect to see pressure mount to find a cure of some kind for aging?
Well, first of all, I don't like to use the word cure. I think that the problem with it is the same as the problem with calling aging a disease, namely that one is, the general public is thereby kind of seduced into thinking that we may at some point develop interventions that you can apply just once. And it's like, getting rid of an infection. And that's not how aging is, because aging, unlike infections, is a side effect of being alive in the first place. It's a side effect of our normal metabolism. And as such, anything that we need to do that stops us from getting sick as we get older is going to be something that is applied periodically. So I don't really like to use the word cure. Of course, there are also problems of other natures, like if you call aging not a disease, that makes people think that it's kind of inherently off limits to medicine and there's no way we'll ever be able to do anything about it at all, which is equally nonsense. But that's the first thing I want to say. Terminology is terribly scary in this field. So then, in terms of the the pressure from the baby boomer generation, I wish it was stronger. The problem with being, let's say 65 or 70, is that by and large, most people who have reached that age have been ground down. They have come to believe that, there's nothing that's ever going to happen, at least not in time for them. And so they become less incentivized to actually, help it to happen sooner. Despite the fact that, they might be able to help their kids. I always used to think it was quite fashionable to care about your kids, but apparently this isn't quite so true as it should be. And in general, the people who support my work philanthropically tend to be in middle age or younger.
Ah, well, so I've read that the average American lifespan is currently 77.3 years old, and demographers are claiming that the maximum possible lifespan is about 125 years old, from what I've read at least. So that is almost double today's average lifespan. Do you think that the boomers have a reasonable chance of living that long, or is medicine simply not there yet?
Well, medicine definitely isn't there yet. The question is whether medicine will be there soon enough for people who are, let's say, 70 today. Now, the first thing I want to say is that different 70-year-olds have very different biological ages. Some people look after themselves better, some people have better genetics, and so on. The people who get to 110, say, which is not very many people, probably only a dozen or so per year, per year of birth date. These are people who have ticked all the boxes. They've got good genetics, obviously. They've also, lived an appropriate lifestyle, especially in terms of management of stress. That turns out to be really important, and maybe some other things. And that's been true all their lives, which means that if you're 70 already, then just things that we can do today, whether it's lifestyle, whether it's supplements, whether it's the kind of small molecule drugs that exist today, it's mighty unlikely that you'll be able to make all that much difference to how long you live or how long you stay healthy based on this. But that's going to change completely when damage repair comes along, when we get to be able to genuinely turn back the clock by restoring the molecular and cellular structure of the body to something like how it was at a younger age. Because then we're actually buying time to progressively improve these interventions, these damage repair interventions. And we can absolutely anticipate that people will be able to completely transcend any biological limits that naturally exist on how long you can stay healthy and how long you can stay alive. That's actually where the term longevity escape velocity comes from.
Ah, okay. Well, as our population ages, this market for life extension supplements is growing, and there are a lot of fads out there. There are so many supplements that don't do anything, right? And that's why I put the disclaimer up front. I don't want people to rush into things and, waste their money or potentially do something harmful, without knowledge, without consulting their doctor. But lately, I have been reading this buzz about NMN, or nicotinamide mononucleotide, and I've also been reading about rapamycin and metformin as life extension drugs. So from a scientific perspective, do these have merit, or are these just the latest in a long fad of supplements?
So let me just talk about rapamycin, because everything I say about rapamycin also applies to these other drugs that you mentioned, these other supplements. But rapamycin is probably the best example. So it's probably the one that kind of poster child of all of this. All of these supplements are, in one way or another, what are called calorie restriction mimetics, which is to say that they trick the body into thinking it's not getting enough calories even if it actually is getting enough calories. And calorie restriction mimetics are very interesting because for nearly a century now, it's been known that calorie restriction itself works really well to extend life in the laboratory. People started doing this to mice in the 1930s, and they found that they could get up to a 50% increase in mouse lifespan by just feeding mice less than they would like. So that's interesting. That's very interesting. And of course, the problem is that people rather like eating, so they don't really want to do calorie restriction. So if you could invent drugs that essentially achieve the same thing without the actual fasting, then you've really got something promising on your hands. But there's a catch, a huge catch, which is that the reason calorie restriction works at all is because famines actually happen in the wild. So in other words, evolution has taken the trouble to develop triggers that sense the calorie intake that one has, and that modulate the metabolic priorities, shall we say, in the body accordingly. In particular, when there's plenty of food, what matters is to grow fast so that you can reproduce before you get eaten. Whereas when there is a lack of food, you want to hunker down and try and survive the famine, because if you grow and you reproduce during the famine, then your offspring are not going to have a chance to grow and reproduce themselves. They're going to starve to death beforehand. So the idea is that evolution has created this, and that's why there are these sensors, mechanisms in the body that sense calorie intake and that respond to it. However, the thing about evolution is it's very clever, but it only does stuff that's worth doing. So, I mean, I'm anthropomorphizing here, but that's for a reason. It's just to communicate what's going on here. Evolution has to have a good enough reason to develop machinery to optimize for particular changes in the environment, such as availability of calories. And that means that it only does so for things that happen often enough. So the problem is that really long famines just don't happen very often, not nearly as often as short famines. And that means that, if you think about it, from the point of view of evolution, a naturally long-lived species is going to evolve less dramatic responses to famine, because it only needs to extend its lifespan by a few percent in order to survive the famines that happen often enough to be worth doing anything for. So what this comes down to is calorie restriction is just going to give humans maybe only a couple of years of extra life, even if you start really early on in life. Whereas, which is obviously only a few percent of human lifespan, rather than the 50% you see in mice. And indeed, that's what we see. People have done these experiments. If you take really short-lived organisms that live only a few weeks, you can multiply their lifespan by a factor of like 5 with calorie restriction. But you can only get a factor of 1.5, 50% with mice. Dogs, it's 10%. Monkeys, it's a few percent if you're lucky. And of course, the point is that the same applies to calorie restriction mimetics. There's no way that you would ever expect a calorie restriction mimetic to do better than calorie restriction itself, because it's activating the same pathways in the body. So that's the caveat. But it certainly does not mean that these interventions like rapamycin are useless. Not at all. First of all, because anything's better than nothing, and also because of health. These things do make you more resilient. They seem to be genuinely good for health. So I'm all in favor of these things. I just want everyone to understand that they are not the Holy Grail.
Well, let me focus in on NMN for a moment. I got excited about this when Dr. David Sinclair started promoting this, but I have read papers hypothesizing that it may improve mitochondrial dysfunction and rescue cellular senescence. This takes us back to your book, The Mitochondrial Free Radical Theory of Aging. And so if I understand things correctly, and I hope that I'm getting this correct, the theory proposes that reactive oxygen species in mitochondria cause damage to macromolecules in the cells and in the mitochondria themselves, such as lipids, proteins, and that all-important mitochondrial DNA. So, one of the things that I've also read, and I'm not sure if I'm getting this correct, is that the big challenge with treating mitochondria, I guess, is actually getting nutrients into them, right? Because they won't accept a lot of molecules.
So no, you haven't really got that right. First of
Okay.
all, back to NMN. So NMN is converted in the body into a molecule called NAD. And NAD, you can't take NAD itself because it's not orally available. It doesn't get through the gut, but NMN does, and so that's basically equivalent. The same is true for nicotinamide riboside, which is another precursor of NAD. Um, now, um, I could go into the molecular details of why increasing the amount of NAD tricks the body into thinking it's in a family when it isn't, but I won't do that because that's not what you asked. The the impact on cellular senescence is, it's likely to there's likely to be some, but the thing about cellular senescence is senescent cells are created all the time in the body, and they exist in many cases for good reasons. They are actually contributors to wound healing, but they need to be eliminated when they've done that kind of job. And the immune system does that, but it doesn't do it completely. Some senescent cells survive, and those are the ones that cause problems. So one thing that calorie restriction and thus something like NMN or rapamycin may do is to enhance the ability of the immune system to get rid of some more of the senescent cells that would not normally be got rid of. But it won't be a complete job. It might somewhat improve the elimination of such cells. With regard to mitochondria, so the mitochondrial free radical theory of aging that I discussed in my book in 1999 is a theory focused entirely on the mitochondrial DNA. The mitochondrion is, of course, made of the same kind of stuff that the rest of the cell is, proteins and lipids and so on. And as you say, the process of respiration, the chemistry of breathing, if you like, creates these things called free radicals, which damage macromolecules of all sorts. Now, the cell has a very nice system for eliminating this damage. Essentially, when a mitochondrion accumulates enough damage to its membranes, which are made of course proteins and lipids, then it gets the whole mitochondrion gets destroyed by a process called
Mm, okay.
mitophagy. Okay, so that's great because then new mitochondria are created, or to be more precise, mitochondria are kind of made to divide, so you have a population of mitochondria. But what I didn't mention in what I just said is the DNA. The DNA can get damaged as well, and you can get mutations in it. And the thing about mutations is that you don't get rid of them by creating new mitochondrial DNA, because the new mitochondrial DNA is created by copying the old DNA, and therefore you end up with a copy of the mutated version. And it turns out that mutated mitochondrial DNA accumulates in the body. And so the essence is to stop that from happening, or to somehow circumvent the consequences of that. Consequences are still very much up for debate, despite the fact that this has been studied for so many decades. But it looks like it causes general systemic problems. It causes cells that get taken over by mutant mitochondrial DNA, are actively toxic to their environment, things like that. So it's not really a matter of nutrients. If it were, we'd be all right. It wouldn't happen because a mitochondrion that can't import stuff won't replicate. They won't be able to take over. It'll be eliminated sometime. I wish that were what happens, but unfortunately, it isn't what happens. These mitochondria survive and they take over, and that's why it's a problem.
Oh, okay. Well, so even if you're able to solve some of these issues, though, this brings us back to the Hayflick limit, right, of something like 40 to 60 cellular divisions. And one of the things that I've wondered is if we're able to essentially clean out our cells more effectively, won't that natural cellular turnover, I mean, just by living, right? We lose cells all the time. Won't that eventually be fatal if we're not able to replace cells that are lost?
So we have to be very careful in looking at the role of cellular senescence in the actual body. The term cellular senescence implies kind of, subliminally that, aging is all about cell division. And honestly, Len Hayflick, lovely guy, fantastic guy, but he really messed up by coining that phrase, because there is very little evidence for this. We certainly see that senescent cells accumulate in the body, but by and large, we believe that this happens not because of what's called replicative senescence, which is the phenomenon that Len Hayflick discovered, where cells get to be in this senescent state before, and as a result of dividing a lot, and their telomeres getting shorter, which was discovered a decade or two later. The main reasons why we see senescent cells are because of stress, because of other kinds of damage to the cell. We know that there are many different ways to induce senescence in cell culture, and we believe that those ways are more prevalent in the body. Then again, though, as I said, senescent cells are mostly eliminated by the immune system. So again, it's not clear that replicative senescence actually matters, even to the extent that it does happen in the body. So I wouldn't worry about Hayflick limit too much. In fact, my view is that we should be manipulating telomeres in the opposite way, with greater benefit, actually to stop them from being maintained through cell division. Because the problem of maintaining telomere length during cell division is that it's what cancers need to do. If a cell gets a lot of mutations that make it divide even when it's not supposed to, which is what cancer is, but its telomeres get shorter every time it divides, then it will never get big enough to be problematic for us. We are big enough animals that a cancer will divide itself into oblivion well before it gets big enough to kill us. This is only true for big animals. For mice, a small cancer can kill a small mouse, right? So actually, mice do not have a Hayflick limit in the same way that we do, because they express this enzyme, this telomere lengthening enzyme called telomerase, in most of their cells, whereas humans exhibit, well, excuse me, they exhibit what I like to call telomere thrift. In other words, they express this enzyme telomerase as little as they can get away with, which in most cells means not at all, because most cells don't divide at all in the body, right? Most cells either are constitutively unable to divide, like, neurons, for example, or heart muscle cells, or else they only divide very occasionally on demand, like, for example, the skin cells in the lower layer of the skin, the dermis. They only divide when there's a wound, kind of thing. The cells that do divide regularly, like, for example, the stem cells that regenerate the epidermis, the upper layer of the skin, or the stem cells in the bone marrow that make the blood, or the stem cells in the gut that make the gut lining, all of those actually express a trace of telomerase, much less than cancer cells do. And that's enough for them to be able to escape the Hayflick limit.
Well, so in terms of telomerase, I appreciate you going on to that, because this brings me to Liz Parrish's work with BioViva. So she used genetically engineered retroviruses to lengthen telomeres and administer myostatin inhibitors for increased performance. Now, this was back in 2015, and I have done, I think, 2 interviews with her, and she did see, again, she sees longer telomeres, but she's also seen increased muscle mass, and so she's had overall good benefits from this. So from what you're saying, though, we probably want to go the opposite direction to avoid cancers.
Yeah, so Liz is one of my favorite people, let me tell you that. I think her contribution to the field since the past 10 years that she's been involved has been absolutely fabulous. And, I've done a lot of work over the years in building the community and introducing people to this whole movement. Liz was one of them, and I'm very, very proud of having been able to do that. The thing is, Liz is in her mid-50s now. She was less than 50, she was in her 40s still when she did this therapy. So, of course, that means that it's somewhat difficult to make a a robust assessment of the impact on biological age, because one's not really going downhill very much. Especially she was already pretty young for her age biologically. She definitely didn't look her age when we first met back in 2013. The impact of follistatin, this myostatin inhibitor, can be measured. As you say, you can have an increase of muscle mass. There's plenty of evidence in other organisms that this should be good for you. Sarcopenia, the loss of muscle during aging, is definitely a big deal. It's something that we need to address. And follistatin looks like the best way to do that of the ways that have been explored so far. Probably better than growth hormone in terms of the quality, not just the actual mass of muscle. Though, I think there's still plenty of research that needs to be done there. But telomerase, yes, you're absolutely right. Liz definitely administered gene therapy for telomerase as well. And, it remains to be seen. But I think it's risky. I think that we should be very cautious about that right now. As I say, mice and humans have very, very, very different telomere biology. Of course, mice and humans have somewhat different biology in pretty much every way. That's why things that work in mice don't always work in humans. In fact, they mostly don't work in humans. But telomere biology is particularly bad in that regard. So the fact that you can extend lifespan using telomerase gene therapy in mice, which was shown a decade ago by a Spanish group and was more recently again shown by collaboration between Liz and George Church, that doesn't tell me anything about humans.
I did want to ask about organisms that don't age, right?
Okay.
And so I think that's important to touch on. Aging is not inevitable. There are simple organisms, right, like the immortal jellyfish, sturdy turtles, or planarian worms that are effectively immortal, right?
Right. Well, not so much the turtles. So, jellyfish, planaria, hydra, yes. These animals, I think we can pretty confidently say that they genuinely do not have aging at all. But there's a reason for that. They are not really organisms in the strict sense that I would like to use the term, because they do not have any constitutively long-lived cells. All of their cell types have the capacity to regenerate. Hydra, for example, as I understand it, there's no cell in a hydra that has spent more than about 3 weeks without dividing. Now, why is that so important? It's important because cell division is spectacularly rejuvenating. What it does is, first of all, if you're accumulating waste products, for example, in the cell, which is definitely, something that cells do, then by cell division, you dilute that waste away, right? You halve the content, right? Similarly, with stuff that can't be diluted because it's genetic, I was explaining about how mitochondrial DNA matters, right? There again, with cell division, you can select away. You can find, the cells that don't have the mutations are ones that do better after progressive cellular generations. So an organism that doesn't have any what are called post-mitotic cells that are long-lived, has a much better chance of not aging than an organism like you and me that has post-mitotic cells. And the thing is, we don't have a choice about this because we have organs that rely for their function on being built from cells that just live a very long time. The brain is obviously the most obvious one. Also the heart, really. The way that heart muscle cells are stitched together kind of precludes the possibility of replacing those cells regularly. So you can't really look too much at these very primitive organisms. But you mentioned turtles as well. Turtles are not the same because they are vertebrates, of course. In other words, they have a heart, they have a brain. I mean, planaria have a kind of brain, but it's a brain that doesn't do nearly so much. What about turtles? Well, my belief, and indeed the belief of nearly everybody in the field, is that turtles do age. They just age really, really slowly. And the same
Mhm.
goes for, rockfish that live a couple of hundred years, or indeed sharks that live a few hundred years. Um, there is an enormous variation in longevity within mammals, for example. And indeed, there are some mammals which are also in this category where they age so slowly that people, some people like to say that they maybe don't age at all, like the naked mole rat. Um, but honestly, the smart money at this point, to be honest, is on the idea that they do age. They just age really slowly because their evolutionary niche, their environment, their ecological niche, is conducive to aging really slowly. And that sometimes means that we may be able to learn from those organisms, but only in very specific ways. So, for example, turtles and rockfish are, of course, cold-blooded. So they already have a, a less difficult aging problem than we have because chemistry just happens more slowly in those organisms. And so aging is bound to happen more slowly just for straightforward biochemical reasons, nothing to do with biology, really. Um, and then whales. Okay, whales live a long time, but they're very, very large. And that's very important because it turns out that being large means you have a low surface to volume ratio. It means that your average cell within a whale needs to burn a lot less energy, a lot less nutrients, calories, in order to stay warm. So they are, of course, warm-blooded, but they can stay warm without burning so much fuel. And as I mentioned earlier, burning fuel creates free radicals, so the less you do of it, the better, by and large. I mean, it's not quite that simple, but close enough. Then naked mole rats. Naked mole rats are mammals, so they're warm-blooded, and they're really small. So, that might be interesting. But again, actually, you know what? Not really. Because in their natural environment, they live in tunnels like 1 yard under the surface of the Kalahari Desert, and it's warm down there, even at night. The temperature fluctuates by like 1 degree centigrade from day to night. So they don't have to heat themselves up very much either. And sure enough, if you try to if you take naked mole rats and you put them at a lower temperature, like 10 or 12 degrees centigrade, then they won't just burn a lot of fuel and stay warm and get warm. They'll just say, all right. They'll just behave as if they were cold-blooded. So they have a different kind of biology in terms of burning fuel than what we do. And we don't really have a choice in terms of changing those fundamental things. That's not quite the whole story, though. There are some things that we may learn. Naked mole rats, for example, have a particularly ingenious method for avoiding cancer, which involves a variation on the way they make something called hyaluronic acid. And people are very interested in studying that and making use of the distinctive HA synthase that exists in naked mole rats. Then, birds are interesting. Birds of a given size tend to live maybe 10 times longer than most rodents, like mice or whatever. And despite the fact that they have a high metabolic rate because they're flapping, right? There's a lot of work involved in being a bird. And so their mitochondria seem to run more cleanly. They don't make as many free radicals as mammals do per amount of energy that they burn. So we might be able to learn something about how that happens, and that might lead to something that we could apply medically.
Wow. There's so much going on here. Well, Aubrey, let me thank you so much for your time today. Again, truly a pleasure and an absolute honor having you with me. And I think that your work is just absolutely stellar. So I cannot give you enough praise. And thank you. Thank you for doing such a tremendous service for
Well, thank you
everyone.
so much, Tim. You're very, very kind. And I know we only got through like a quarter of your questions because I was getting long answers, but I thought it was probably best to give,
Oh, no, no, it's
in-depth
absolutely
answers.
wonderful. So I want to close by asking what is coming up for you and how can people get involved to help move your work, help move the LEV Foundation forward, help make all of this a reality?
Well, thank you for asking. Yeah, I mean, LEV Foundation is is doing unique work that I believe is the most impactful work in the field right now in terms of the amount of information that we gain per dollar spent. It's something that absolutely needs to be done. Nobody else is doing it. And honestly, that is fundamentally the problem. We do need money for this. These experiments involve each of these experiments. We're doing the first one right now. They involve 1,000 mice. And the interventions themselves, the gene therapies, the cell therapies are also quite expensive. So, this experiment we're doing right now costs $3.5 million. And, it's hard to get people, it's hard to make that money through philanthropy, but that's what we're trying to do. So anyone who wants to help to build up our war chest so that we can get the next experiment going as soon as possible, I will be eternally grateful. Of course, getting hold of us is easy. I'm sure you'll put our website in the show
Absolutely.
notes, and my email address as well, aubrey@levf.org. So, yeah, anyone who wants to get in touch, please do so.
Wonderful. Aubrey, thank you again so much for your time today, sir.
Pleasure. Pleasure. Thank you for having me.